Hi everyone, I am Ajir and today I am with you with another subject which is the line integral of scalar functions and vector field which we proposed in first single calculus in R on interval a to p, and the second for plane curves in R2, and the third for space curves in R3. The application of line integral can be worked on by a force in moving an object along the curve. In single calculus variable, if we have a force which is defined by fx, and if we apply on an object, for example, if we consider this object and we apply the force over this as fx, and we move these objects along the interval, for example, from the point A to B. So the work done is multiplication of the force in the distance. If we divide this interval to union of the equal interval, for example, from the point xi to xi plus 1, I consider this as delta xi. So work in this point, if consider here is fxi, and here the work will be fxi plus 1. And always in every point, the work in the point I is equal to multiplication of the force in the distance, delta xi. So if we get the summation, because we want to calculate from the point A to B, so it will be the summation of fxi in delta x, which is changed from I1 to n when n approach to infinity. So this will be present as the integral from initial point A to B fx dx. For example, if we want to evaluate the work done by force fx on an object moving from point 11, so will be equal to integral from 2 to 11 fx dE, and very easy in the single calculus we can calculate this integral. This from 2 to 11, which is equal to 1 over 3. Line integrals for a scalar function in the plane. Let's explain the concept of line integral within these figures. If you consider these fx and y as a scalar function and the curve C here, the area which here intersects with a scalar function f, this define the line integral of f over curve C. Let's see how we can get this. If I have this curve C and from the initial point A to B, we divide the curve C within equal part with equal distances. So here if we divide to n part, and for example the 2 points xi and xi plus 1, from the point xi I come up the line which intersects the function f, and also for xi plus 1 also parallel to y-axis I consider this line. This area it is a rectangle which if for any points I come up with this line, we see that we have equal lines, so we can divide this area to n parts, and sum of all of this area will define the line integral. As all of these parts has same area, if I consider for xi and xi plus 1, here we have the curve C, and here which intersect with real valued function f is supreme, and for supreme, if I consider the tangent over this curve. For example, this one is supreme, or here is delta si. And I write here, for example, for this curve, I consider the tangent to the curve C, it is supreme to this point, is r prime in the point T. And if I consider two parallel line with y-axis and x-axis, here will be the xi and here the yi, and according to this triangle, this side will be radical dxi2 plus dyi2, which exactly is the si. And here I want just for xi and xi plus 1. So we want to calculate this area. Here for every point if we come up for xi, we have f xi and here f xi plus 1. So in this distance, for every point to compute the line integral, so we multiply this f for xi and xi plus 1, f x and y multiply in delta si. And then we sum all of these together from I equal to 1 to n. And this limit gives us the integral of fx and y multiply in ds. And over the area which from A to B. So here we define for a scalar function f, if f be defined on a smooth curve C, the line integral of f along C will be defined by integral of fx and y ds, which is this limit like before we explained. And if the limit exists here, the si is equal to this radical. And for the curve C, which is parameterized as xt and yt, just we compose with curve C and multiply in ds, which is equal to x prime 2 plus y prime 2 dt. Sometimes the curve which we want to compute the line integral is not one smooth curve. Sometimes is union of some piecewise smooth curves. For example, some curves like this, maybe this is one parametric equation and another one different, or sometimes we have a different piece of curves. For example, here C1, here C2 with different equation. Here we have a circle, here another one. So we define and refer to this definition if we have a union of piecewise curves. In this case, forget the integral of function f over this curve. We have to sum all of the line integral over every piece. Let's come within an example and let's see how we can compute this line integral. In this example, we want to evaluate the integral of 2x ds, where C consists of two curves, C1 and C2. C1 is parabola, y is equal to x2 from 0 and 0 to 1 and 1, followed by vertical line segment C2 from 1 and 1 to 1 and 2. The first parameterization for the parabola curve y is equal to x2 will defined by C1, which I can write R1t is equal to, if I consider xt, so y is equal to t2. And the t change between 0 and 1. And curve C2 also is a vertical line segment C2, which I consider R2 x equal to 1, and I can write y as t t equal between 1 and 2 will change. So t between 1 and 2. Now we going to evaluate the integral formula for f, x and y ds, which we compose with the curve. For every curve, then union of this curve, we have the two summation of two integral. Integral over the c1 if c1 multiply in supreme 1, norm of supreme 1, which is exactly arc length of c1 over c1t, to change between 0 and 1. So integral over f c1 r1 and the norm of r1 r prime, and over c2 is f r2 multiply norm of r prime 2 dt. For first we put f composed with c or r1 is this function. We get the derivative of r1 to get the arc length. So the norm of r prime 1 will be radical 1 power 2 plus 2t power 2, which is 4t. And also for c2, if we get derivative of r2, we will have 0 and 1, and norm will be 1. Now we continue with this integral over c1, t between 0 and 1, and f composed with the curve r1, which is 2x. Instead x we will put 2t, and we will have 2t multiply in norm of r prime 1, which is radical 1 plus 4t plus integral between 1 and 2 multiply in 2x. X is equal to 1. It was the vertical axis, and 2 multiply in the norm of r prime 2, which is 1. And so we can very easy get this integral by considering change of 1 plus 42 as u. If we suppose this is equal to u, so derivative will be 8 dt equal to du. Now we replace by t in term of u, so we will have 2 over 8, which is after 1 over 4 radical u du, and plus integral of 2 is 2 t between 2 1, so 2 multiply 2 minus 1, it is 2. And now we get this integral will be 1 over 4 multiply 1 over, because its power is 1 over 2, so we will have 1 over 2 plus 1 is 3 over 2 u power 3 over 2 plus 2, and then we can replace u by 1 plus 4 t2. Now 4 and 2 will be deleted. We will have 1 over 6 1 plus 4 u2 42 power 3 over 2 plus 2, and t also change between 0 and 1. If we put 1, we will get 5 here, 1 over 6, 5 power 3 over 2, which I write as radical. And if I put 0 instead of t, I will get 1 minus 1 plus 2. So here we can get by hand this answer. Let's we go within the Maple and we compute. For Maple software for a scalar function, if we want to get the line integral first, we write restart to clean the other problems before we run. Now we start with students, and then we define the line integral. L will be the capital, but I for int will be the small. I just recommend that after for the vector field I will be, so the line int, here we should write the function. The function is 2x, and then we have to write the curve. Here we have two curves, C1 and C2. C1 was actually the parabola of y equal to x2, which we write as a pad. So we write the pad of t and t2, t between 0 and 1. We can run, or even we can plus with another line integral. So again we add the line int of 2x, same function, over that segment which was the vertical line of x equal to 1 and t. So now I can write again as a pad of 1 and t change between 1 and now we can run it, and here we get this integral. And if we want to get evaluation of this integral, we write eval of, we can put the name for previous statement, or even I can put the percent to calculate. I put a and I write eval of a, then we run. So here we will see that our answer is 3 points, this one. And if we evaluate what we get from this by hand, 1 over 6, this radical plus 2, and I want to check whether our answer is same. So again I eval 1 over 4 multiply in radical 5 over 3 minus 1 plus, now we run, and we see that we have the same answer as before. In continuation of line integrals for space also, definition is same as for two dimension, just the differences here as you see. We add just the parameter z more, even in this formula also and here also. And for the integral, we have the same integral of f composed with the curves RT multiply in the norm of R prime, which we can compute by these square roots of x prime power 2 plus y prime power 2 plus z prime power 2. For a space problem, I consider this. We want to evaluate the integral of y sine z. So our equation is this, and the curve is in 3 dimensions as cosine, sine, and t. So according to the formula, we have to integral of f rt multiply in norm of r prime t dt. F is y sine z, then we compute with composite. We have y, so instead y we will put sine t. Instead sine z we will put t, so again sine t multiply, and the norm of r prime t, rt is equal to this, and r prime here will be minus sine t, cosine t, and 1. So the norm will be radical sine t power 2 plus cosine t power 2, which is 1 plus 1 dt. Here just we have sine 2t. Very easy, we can compute by converting this formula to cosine. So we will have 1 minus cosine 2t over 2 multiply in radical 2 dt from t change between 0 and 2 pi. So here we can compute it, 1 over 2 radical 2 t minus integral of cosine is sine t. So this will be appear in the denominator. So we will have minus 1 over 4 sine 2t. After replacing by this, we will get radical 2 pi, and here will be appear 0.